Okay, let's turn next to the variance and the standard error of the slope coefficient. And it actually should be a little bit easier, as you can see if you jump to the next slide. And yeah, but I also want to just derive it again step by step, but that should be easier. So what we want to show is what's the variance of the slope coefficient b. And what we derived is that the slope coefficient is the sum of the covariance of x and y, and it can be written as xi minus x bar times yi minus y bar. So that's the covariance between x and y, and then we need to divide that by the variance of x. And the variance of x can be written as the sum of xi minus x bar squared. And then we still would have to divide both by n minus 1, but that will cancel out. Okay, then what we did is we derived the ki. Let's just do that again. So the ki we derived by saying, you know what, let's multiply that through. But if we multiply something by y bar times xi minus x bar, then this will sum up to 0. The xi minus x bar will sum up to 0, and then we'll make our life a little bit easier. So let's start with the second term, and then multiply yi times the first parentheses. And that is the sum of yi times xi minus x bar. Okay, and then I multiply xi minus x bar times y bar, and because y bar has a minus, there's a minus in front. So minus y bar. And then if I already put the sum sign in front of xi minus x bar, I get the sum of xi minus x bar. But the sum of xi minus x bar, that's the sum of all the deviations from the mean, we know they are 0. So that's why we can cancel that. And our formula simplifies a little bit to the sum of yi times xi minus x bar over the sum of xi minus x bar squared. And then we said, and I think I explained that earlier, that we always assume we get the same x's in every sample, but we have different y's. So in the example with the relationship between shoe size and people's height, we assume we always get the same number of people with a shoe size 7, shoe size 8, shoe size 9. The only variation occurs in the y. So that's why this red becomes a constant, and our variance of b can then be simplified to the sum of yi times ki, with ki being xi minus x bar over the sum of xi minus x bar. Okay, so, and then also earlier we said whenever we have a constant times a random variable. So even though there's some randomness in ki, we treat it like a constant. So now we know that our variance of b, so this is basically, okay, so earlier we said that the variance of a constant times a random variable, that becomes equal to the sum of the constant squared times the variance of the random variable. Well, we do the same now here. So this would be basically, we treat ki like a c, and yi is actually our random variable. So that means the variance of b can be written as the sum of the variance of ci, the variance of yi, times ki squared. Okay, and also in the previous video I already explained that the variance yi is also assumed to be constant. So that means the deviations around different trend lines is always the same. So what we need to evaluate is essentially the variance of yi, which is the variance of the regression times the sum of ki. Okay, so all we need to focus on is now this term here. So the sum of ki is equal to, and by the way, it's ki squared. I forgot that one, because c squared. So that means we have, again, and we had a similar case already before, xi minus x bar squared. And so now, and there's also squared. So now in the denominator, we basically have the sum of xi minus x bar squared, but then we have to square that entire term, so we can either put here parentheses around and do it like this, or we just write it twice as a product. Well, and then we see that once it cancels out, and this term becomes simply 1 over the sum of xi minus x bar, and then the parentheses, squared. Okay, so now we have the sum of ki squared, and we have the standard errors, and we have the variance. So now we know that the variance of b is simply the sum of yi minus y hat squared over n minus 2, because that's what the variance of y is. That's the variance of the regression times 1 over the sum of all the xi minus x bar squared. Well, a regression output of a statistical software program like Excel will not report the variance but the standard error, just as before. So the standard error is the standard error of B is now again the square root of the variance of B, and that is, so we can first take the square root of this one, and we know that this is the standard error of the regression. So the first term becomes the standard error of the regression, which I call yx, times 1 over this, so we can just write it over the square root of the sum of xi minus x bar squared. And that's it. So that is the standard error of B. So, and you see both standard errors, they take advantage of, so both the standard errors of the intercept and the slope coefficient, they take advantage of the standard error of the regression. So anyhow, let's see if that's the same, and you see if you go through the slide and you see we arrive at the same result, the standard error. I mean, I call that here x/y or y/x, it's the same. It's the standard error of the regression over the square root of xi minus x bar squared. So those are the same results. So now we can stop here, and what we do next is we go back to the example with which we started the lecture, and let's see and let's calculate everything what we already know how to calculate it, like the intercept, the slope, the standard error of the regression, the standard error of the slope coefficient, and the standard error of the intercept. And then we can double check with an Excel output and see if those formulas are actually correct. And if so, then we know what Excel is actually doing. But let's just stop here, and then let's continue in the next video with applying the formulas to the example.